All right, so we've gone through all of these different inverse trig functions. Now let's look at the different ways that we can evaluate expressions using them. So this first example here is very similar to those that we did in each of the videos for sine, cosine, tangent, but let's just get some more practice with these. So what this one's asking for is, so it's inverse sine, so we're looking to find an angle where, and then inside the function is our y-coordinate. Since it's the inverse of sine, we're working with the y-coordinate of positive root 3 over 2. So what I'm going to do is just have a picture of the unit circle to help me out. And what I need to keep in mind is that with sine, we can only be from negative pi over 2 to positive pi over 2. And since the y value is positive, that means I'm going to be up here in the first quadrant. So root 3 over 2 is going to relate to pi over 6. So we could be there or there. This y-coordinate is the long side. So that means I'm going to have kind of this tall case here, where x would be positive 1/2, y would be root 3 over 2. So this is our location because of that y-coordinate of positive root 3 over 2. So what I need to do is find that angle measurement. That's what we're solving for here. So it's like 1 pi over 6, 2 pi over 6, or that's our pi over 3. So this inverse sine of root 3 over 2 is equal to pi over 3. And we're done. Inverse cosine. So with inverse cosine, we're looking to find an angle where, since it's cosine, we're looking at our x-coordinate of 1/2. So if I draw my unit circle, and then with cosine, we only have angle measurements 0 to pi. And since cosine is positive, or my x-coordinate is positive, we're going to be in this first quadrant. And then with a value of 1/2, we're either going to be at pi over 6 or pi over 3. And this actually connects to the one we just looked at. So this is saying x is the short side. So that's coming through right there at 1/2 root 3 over 2. So that actually is the same coordinate as that first example. So we're at pi over 3 again. So our solution, inverse cosine of 1/2 is equal to the angle measurement of pi over 3. And with inverse tangent, so we're looking to find the angle measurement where our ratio y over x is equal to -1. So this tells me that my x and y coordinates are the same, which is happening at that root 2 over 2 coordinates. It's also negative, so that's going to tell me which quadrant I'm working in. So if I have my unit circle, and tangent's restricted from negative pi over 2 to pi over 2, and since that's negative, we're going to have to be in this fourth quadrant where we have positive x and negative y. And these values of 1 are going to be occurring at increments of pi over 4. So we're going to be down here at positive root 2 over 2, negative root 2 over 2. So when we divide those, we would get a -1. So that angle measurement right there is negative pi over 4. So inverse tangent of -1 is equal to that angle measurement, negative pi over 4. All right, so those are cases where we're just calculating the inverse trig function given an input value. But what if we kind of turned it into an equation? So with this case, it's inverse sine, which means what would be inside the function there is a y-coordinate. And then the output that they're giving is an angle measurement. And we're trying to solve for x here. Which again, that x and y, just think of that as a variable. I could have made that any letter right there. The idea is that it represents a y-coordinate because it's within inverse sine. So what this means, oops, here's my circle. is, if I'm on the unit circle, they're giving us the angle measurement. So we're at pi over 6. So they're telling us where our terminal side is. And what we want to know is, what is the y-coordinate? So this is at root 3 over 2, 1/2. And if I want to solve for x, I need that y-coordinate. So x is equal to 1/2, and that would be the end of it. The idea being that if you plugged in arc sine of 1/2, you'll get out pi over 6. Now, notice that this routine is how we have worked with trig functions originally. That idea of we have the angle measurement, find the coordinate. And that's because I could have rearranged this in this form where it's like I don't know the input, but I know the output. Well, if I switched that to our original form where it's like we know the angle measurement, well, if we want to plug in the angle measurement, we would just plug that into our original function, and then it's like I'm solving for what that value would be. So it would be that same routine of look at your angle measurement of pi over 6. Since it's sine, we want to grab the y-coordinate, and that would be that 1/2 there. So you can kind of switch between these two forms, but they accomplish the same thing, and you'd be at the same location within the unit circle. With this one here, what I would need to do is isolate that inverse cosine expression. So what I'm going to do is divide both sides by 3. And what this will give me is inverse cosine of x is equal to pi over 3. So similar to that last case, this is where we're looking for our x coordinate, but we know our angle. So what I could do is I could think of this as the same thing as taking cosine of pi over 3 and solving that. So it would be going to the unit circle and going to pi over 3, which is up here. And that would be a 1/2 root 3 over 2. And then since I'm looking for cosine, I would just grab the x coordinate. So x is equal to 1/2. All right, let's look at some cases with our triangles. So we're going to solve these triangles, which means we're going to find 2 angle measurements. We're going to find that one too, and we're going to find this side length right here. So first thing we're going to do is focus being at this angle measurement, which means that would be opposite. This would be adjacent, and this would be hypotenuse. So something I'm going to note is that I know adjacent, I know hypotenuse, which makes me want to start with working with cosine in some form. I know that my ratio of adjacent over hypotenuse works with cosine. Now what's different here is that I know adjacent over hypotenuse would be 9 over 12. What I don't know is the angle measurement. So if I just plugged into cosine in this form, it's like cosine of theta is equal to 9 over 12. However, in that form, I can't do much. I'm stuck. The idea is that I want to find an angle measurement. So that's where we switch to inverse trig, because I want to find that angle measurement. So how I would switch this is changing to, I want to solve inverse cosine, where the input, and so far, and I mentioned these when I first introduced the inverse trig functions, how we could work with these with right triangles, we just haven't done it yet. So this is where it comes in. It isn't necessarily that the input is the x coordinate on the unit circle, though that idea is absolutely there. It's more that the input for our function here is this ratio of adjacent over hypotenuse. So with the inverse cosine function here, it's like I'm taking inverse cosine. Inside, I'm seeing that ratio of adjacent over hypotenuse, and what we're solving for is the angle measurement. So for us, this would be 9 over 12, and that is going to be equal to the angle measurement. Now, in these cases, if they don't specify, typically we're working in degree mode here, just because with geometric shapes, we usually describe it in degrees, whereas with evaluating and working with a unit circle, we're typically working in radians. So there's this kind of nuance to it. So I'm going to be switching to degree mode here as we work through these triangles. So with this, I just plug into the calculator. So I'm going to go to the calculator and find inverse cosine of 9/12 because 9/12 isn't a nice number on our unit circle, so we need to use our calculator. So inverse cosine of 9/12, and that's giving us 41.41962. I'm going to I'm in degree mode, so that measurement would be in degrees. I'm going to go ahead and take that to 1 decimal place. So I'm going to call that a 41.4 degrees. So what I have there is 41.4 degrees. Now to get the other angle measurement, I'm just taking 180 minus 90 minus 41.4, since all three of those angles should add up to 180. So if we plug that in, oops, don't want to do that there. 48.6. So this angle measurement up here is 48.6 degrees. And then this missing side, I'm just going to use the Pythagorean Theorem to solve for it. So we would have our hypotenuse squared is equal to 9 squared plus that unknown side squared. 144 equals 81 plus x squared. X squared is equal to 144 minus 81, which is 63. Square root of both sides. And let's see, 63 is divisible, sorry, I'm just thinking about reducing down. 63 is divisible by 9, so I'm thinking of a 9 times 7. Square root of 9 is 3, and we'd still have that 7 trapped underneath. So if we wanted the exact value, that works. If we want the decimal form, we could call it a 7.94. So whichever form they ask for, I just want to make sure you can find both. Let's call that a 7.94. All right, so that solved the triangle. The idea is that if we weren't given any angle measurements, we're going to need to use inverse trig in order to find it. Let's do one more. Oh, I shouldn't have written all that over there. Let me just get rid of this. All right, we are standing at this angle right here, which would make this opposite hypotenuse. And then we're missing the adjacent side. We could solve for that just to get it. We could use the Pythagorean theorem. So 10 squared equals 6 squared plus x squared. 100 minus 36 is 64. Let's see, 64 is divisible by 16 and square root of 64 is 8. That's a nice one. All right, so we're gonna have a side length of 8 there. Then we get stuck because we need to find our angle measurements. So as soon as I'm thinking that I need to find an angle, that's gonna send me to inverse trig. So there's a strong relationship there. If we're looking for side lengths, and so if we have missing side lengths and we can't just jump into the Pythagorean theorem, you'll want to use the standard trig functions, just sine, cosine, tangent. So if you're looking to solve for values out here, but you're stuck and can't use the Pythagorean theorem, sine, cosine, tangent. If you're looking inside and trying to solve for these angle measurements, inverse sine, inverse cosine, inverse tangent. That's how these will work together. All right, so we have opposite and hypotenuse, which is telling me that I want to use inverse sine. And inside this will go, like we've been plugging in our y coordinate, but similarly, it's also this ratio of opposite over hypotenuse. And that's going to equal that angle measurement of theta. And from there, I just go to the calculator. So inverse sine of 6/10 will give, and I'm in degree mode, just making sure. If you're in radian mode, like you'll be getting a lot of small numbers typically in radian mode. So it should be kind of a sign to double check the mode that you're in if you're getting like less than 1 degree. I mean, it's not impossible for that to happen in a triangle, but just double check degree radian mode each time. So this is 36.9 degrees. So we have 36.9 degrees, and then we just need to solve for that last angle, which would be 53.1 degrees. And we've solved our right triangle. All right, so there's some different ways that we can apply our inverse trig functions, just evaluating and looking on the unit circle, maybe a little bit of solving to do, which can sometimes be easier to switch to our standard mode if you know the angle measurement but are trying to find the coordinate. That's how we just use standard cosine, standard sine. And then solving triangles when you're looking to solve for the angle measurements, which we hadn't done yet. That's where inverse trig comes in.